Section 10.2 homework, part 1. Analytically show that the equations below represent trig identity statements. That means we need to make the left and the right side equal to each other. Looking at number 1, I recognize that 1 minus cosine squared of theta, well, that is the same as sine squared of theta. Then I know that secant squared of theta is the same as 1 over cosine squared of theta. Multiplying a fraction times a whole number, the fraction being 1 over cosine squared, the whole number being sine squared, you multiply the sine squared times the top only. And I know that sine over cosine is tangent, therefore sine squared over cosine squared is tangent squared. That's what the right side was all along. So, finished. Number 2. I'm going to work with the left side since it's more complicated. I'm going to distribute. So I got cosine of x times secant of x minus cosine of x times cosine of x. Cosine times secant, those are reciprocals. If you multiply two reciprocals, you get 1. Cosine times cosine is cosine squared. I recognize that 1 minus cosine squared is sine squared of x. That's the first Pythagorean identity. That's what the right side was all along. Finished. Number 3. I'm going to change everything in terms of sine and cosine on the left side of the equation. See what that does for me. In order to multiply these together, it's going to be sine squared over cosine. So in order to have common denominators, I'm going to multiply this cosine over here by 1 in the form of cosine over cosine. That way we have common denominators. That's going to give us cosine squared of theta plus sine squared of theta over cosine of theta. That's me adding the two fractions together. Now the top is the first Pythagorean identity, which cosine squared of theta plus sine squared of theta, that's equivalent to 1. 1 over cosine of theta is the same as secant of theta. The right side was secant of theta all along, so that problem is also now finished. Number 4. This looks like a bit of a mess. Left side's more complicated. I'm going to start with it. I'm going to distribute the 1, and I'm going to get cosecant of theta plus cotangent of theta. I'm going to distribute the minus cosine. I'm going to get minus cosine of alpha, cosecant of alpha, times the negative cosine of alpha, cotangent of alpha. I'm going to then change everything in terms of sine and cosine and see what good things happen. Cosecant of alpha is 1 over sine of alpha. Cotangent of alpha is cosine of alpha over sine of alpha. Cosine of alpha is already in terms of sine. Cosecant would be 1 over sine of alpha. Cosine of alpha is already in terms of cosine. Cotangent, we're going to write it as cosine of alpha over sine of alpha. Each of these fractions have sine on the bottom, so they already have common denominators. So if I look closely, this fraction and this fraction are the same, one's plus and one's a minus. So they cancel, which really means that I have these two terms left. If I put those together in one fraction, it's going to be 1 minus cosine squared of alpha over sine of alpha. Oh, I wonder where you've seen 1 minus cosine squared of alpha before. That's the first Pythagorean identity solved for sine. So we can, for sine squared, I should say. So that's sine squared over sine. And we can divide top and bottom by a sine. It's going to cancel a sine on the top and a sine on the bottom, and we're left with sine of alpha. Now the right side of the equation was cosine of alpha times tangent. I'm going to change tangent to sine over cosine. cosines cancel, and we're left with sine of alpha is sine of alpha. Finished. Let's go to number 5. I assume it's the same instructions because there's no new instructions written. Going to distribute the sine and see what that does for me. Sine of x times cosecant of x, that's going to be 1. Sine times sine is sine squared of x times secant squared of x. Once again, this is 1 because you're multiplying two reciprocals. Changing secant to in terms of sine or cosine is going to be 1 over cosine squared. That makes the left side of the equation 1 plus sine squared of x over cosine squared of x. That's just multiplying a whole number sine squared of x times a fraction 1 over cosine squared of x. Sine over cosine is tangent. So if sine and cosine are both squared, it's going to be tangent squared. This is the second Pythagorean identity. 1 plus tangent squared of x is secant squared of x. The right side was secant squared of x all along. Number 6. Once again, I like to use the more complicated side first, which is the left. I'm going to change this to be in terms of sine and cosine. It's going to be 1 over cosine squared of theta plus 1 over sine squared of theta. Leave the right side alone. Or to add those together, I'm going to have to get common denominators. So I'm going to multiply this by 1 in the form of sine squared over sine squared of theta. I'm going to multiply this by cosine squared of theta over cosine squared of theta. That's going to give me this fraction that is sine squared of theta plus cosine squared of theta, it looks familiar, over sine squared of theta cosine squared of theta. Sine squared plus cosine squared is 1. The right side of the equation doesn't have any fractions. So that means the left side shouldn't have any fractions. The reciprocal of 1 over sine squared is cosecant squared of theta. The reciprocal of 1 over cosine squared is secant squared of theta. Now that's close to the right side, but these need to be switched around. That's the commutative property of equality. And that's what the right side was all along. Remember, you're finished when the left and right sides are the same. They are the same, so we're finished. Number 7. Left side's more complicated, so I'm going to work with that. I'm going to add these two fractions together by getting common denominators. So I'm going to multiply the fraction on the left by 1 in the form of 1 plus secant of theta over 1 plus secant of theta. Fraction on the right, I'm going to multiply by tangent of theta on the top and bottom. That's going to give me 1 plus secant of theta times 1 plus secant of theta plus tangent squared of theta. My denominator, 1 plus secant of theta times tangent of theta. Now, a lot of times multiplying out the denominator isn't very useful. Depends on the problem whether it is. I'm going to hold off on multiplying that out just in case it's not useful. This product, multiplying two binomials that are the same, that's going to be a perfect squared trinomial, which is going to be 1 plus 2 times secant of theta plus secant squared of theta. Bring down the plus tangent squared of theta. Bring down my denominator that was before, because I'm going to leave that alone for now. Looking at this, I got a lot of secants in this problem, so I might as well make the entire top secants. How can I change tangent squared to be secant? Well, I can't that easily, but if I include the 1 with it, 1 plus tangent squared is the same as secant squared. That's one of the Pythagorean identities, the second one to be exact. Denominator doesn't change. I am running out of space quickly. Fortunately for me, I can just make this smaller. Or can I? Come on, little fella. There we go. Now if I combine like terms, this and this are like terms. There are two of those. So I have 2 secant of theta. Oh boy, dyslexia in full force right now. Plus 2 secant squared of theta. Denominator hasn't changed. Also, the right side hasn't changed at this point. Now I can factor out of the numerator 2 secant. That's a GCF. That's common with both of those terms. I'm going to continue a little bit down here, then I'm going to have to take up some more space up top. So if I GCF a 2 secant out of this, 2 secant of theta, I'm left with 1 plus secant of theta. Now the bottom has a 1 plus, sorry, this wouldn't be squared. If I factor out a secant out of secant squared, we're just left with the secant. These cancel. They're multiplying the same thing by the top and the bottom. I'm going to continue this up here. So I got 2 times secant of theta over tangent of theta. Now at this point, I'm going to change everything in terms of sine and cosine. Actually, before I do that, I'm going to rewrite this so it's not a fraction. So this is the same as 2 times secant of theta times cotangent of theta. I just reciprocated tangent. Reciprocal of tangent is cotangent. That moves it to the top. And then secant is 1 over cosine of theta. Cotangent is cosine of theta over sine of theta. Cosines cancel. So now we got 2 times 1 over sine. Sine is the same as 1 over sine is the same as cosecant. And that's what the right side was all along. So we have proven that that's an identity. Number 8. If theta equals pi over 4, numerically show that the following equations are identities by finding the exact values of each expression. Show your work and leave your answer with rationalized denominators. All right. So we're going to have cosine of pi over 4 plus sine of pi over 4 times tangent of pi over 4. That should be equal to secant of pi over 4. Let me just remind you about pi over 4. Pi over 4 is in quadrant 1, also known as a 45-degree angle. So we could think of this in a few different ways. We could think of this as the radius is 1 and each of the legs square root of 2 over 2. Or if you prefer, you can think of each of the legs as 1 and the hypotenuse is square root of 2. Either way, good things are going to happen. Cosine of pi over 4 then is going to be square root of 2 over 2. It's the x value in the unit circle. Or if you use this bottom triangle, it's x over r, which is 1 over the square root of 2, which when rationalized is square root of 2 over 2. Sine of pi over 4 is also square root of 2 over 2. Tangent of pi over 4 is square root of 2 over 2 divided by itself, which is 1. This equals secant of pi over 4. Secant is the reciprocal of sine, so that's going to be 1 over the square root of 2. Pardon me. It's going to be this reciprocal, which is 2 over the square root of 2, which when you rationalize that, that ends up being something real nice. So we got square root of 2 over 2 plus square root of 2 over 2. If we rationalize this fella, multiply the top and bottom by the square root of 2, we're going to get 2 square roots of 2 over 2, which reduces to square root of 2. On the left, if you add those two fractions, we're going to have 2 of these. 2's cancel, so you get square root of 2 equals square root of 2. So it checks out. Same directions for number 9. We're supposed to put in pi over 4 in for our thetas. So we got sine squared of pi over 4 divided by cosine of pi over 4. That should be equal to secant of pi over 4 minus cosine of pi over 4. Sine of pi over 4 is square root of 2 over 2. That's supposed to be squared. Cosine of pi over 4 is square root of 2 over 2. Secant of pi over 4, we just found out, was just square root of 2. If you reciprocate this and rationalize it, that's what you get. And cosine of pi over 4 is square root of 2 over 2. If you simplify the left side, square root of 2 squared is 2. 2 squared is 4. On the bottom, we got square root of 2 over 2. On the right, if we get common denominators, we're going to get this ugly fella. On the left, if you want to get rid of your complex fraction, we can multiply the top and bottom by 4, same as multiplying by 1. Those 4's cancel. That cancels and we get a 2. This is 2 over 2 square roots of 2. Running out of space again. I should have given you more space for this. My apologies. Supposed to rationalize the denominator, the direction said. So we're going to multiply top and bottom by the square root of 2. It's going to give us 2 square roots of 2 over 2 times 2. These 2's cancel, which ends up giving us square root of 2 over 2. Over here on the right, we got 2 square roots of 2 minus 1 square root of 2 over 2. So if we get 2 square roots of 2 and we take 1 away, we're going to be left with one of them. And that's what the left side was for a little while. That concludes the homework. Hope you enjoyed it as much as I